In the last lecture, I talked about how programming was done back when computers were first invented in the 40s. So basically, to write a program, you had to flip switches. So for instance, a switch that was on would represent a 0. A switch that is open would represent a 0, and a switch that is closed would represent a 1. And we all know that our computer or processor is only capable of understanding what zeros and ones mean, right? So suppose to add two numbers, a programmer would have to input the following sets of zeros and ones by flipping certain switches, right? So suppose a specific set of switches here would be open. Basically, a specific switch would be open here, the next switch would be closed here, and so on. So this is known as machine code. So back in the days, that is how you had to write a program. So if you wanted to, suppose, say, add two numbers, you would have to input a number of zeros and ones like this. So this was pretty difficult from a programmer's perspective. So to make things easier, a higher level language, which is known as assembly language, was invented. An assembly language is basically a human readable version of machine code. So an assembly language that could say add two numbers would look something like this. So basically, let's assume that these are two locations, and the summation of the data in these locations are stored here. So afterwards, what we now call high level language was invented. So an example would be C, C++, Java, etc. So in a high level language, to add two numbers and store it in a particular variable, it would look something like this, right? But at the end of the day, your computer is only capable of understanding zeros and ones. So this high level language that you write as a programmer has to be converted. So there are a number of steps that take place during this conversion. So first up, your high level language has to be converted to assembly language using what is known as a compiler. So your compiler converts your high level language to assembly language, but still your computer or processor does not understand assembly language, since it's ultimately written in English or in ASCII value. So your assembly language is then converted by a programmer known as an assembler to machine code. It's converted by your assembler to machine code, and this is what your CPU is capable of understanding, right? So we talked about this in the last lecture. So starting from today, we're going to learn an assembly language which is known as MIPS. So MIPS stands for microprocessor without interlocked, pipelined stages. So the full form of MIPS sounds pretty daunting, but we'll learn about what each of this means later down the course. So before I walk you through what MIPS is, so MIPS, so far I've mentioned that it is an assembly language, and it is based on the RISC architecture, which stands for Reduced Instruction Set Computer, and we talked about in great detail in an entire video about the RISC architecture. So RISC is an instruction set. Okay. So before I start talking about MIPS, you have to first understand the concept of memory. So memory can be of two types. I'm calling the first type register and the other data or instruction. So you see, registers are very fast units of memory. They are basically the fastest. So suppose if you want to add two numbers, so you have, the way your computer achieves this operation is that it brings out two numbers from your registers, adds them, and suppose stores them in a register as well. So everything, all the operations that your CPU executes is basically done from the register. So obviously your register has very limited space and it cannot possibly hold all the data that you might need. So as a result, there is transfer from this type of memory to this one, basically from the data/instruction memory to register. So now what do I mean by data? So data could be, suppose, the value of any variable. It could be something like 5 or 5101, something like that. An instruction is basically, suppose, an assembly language instruction, suppose one that looks like this, for instance. So your instruction and data are in the same memory. So we're learning about MIPS in this course. So let us talk about the MIPS data/instruction memory. So in MIPS, your memory has addressable spaces like this. Okay, so each of this space is exactly 1 byte or 8 bits. So you can basically store 8 bits of data here. So this is the MIPS memory. So how many of these 8 bits or 1 bit of addressable spaces are there in MIPS? Well, as it turns out, there are 2 to the power 32 of these locations. So now, can you calculate the memory size of MIPS? How would you do that? You know there are 2 to the power 32 addressable spaces and each space is 1 byte. So that means the size of MIPS memory is 2 to the power 32 bytes. So the question is, can you now convert this to a smaller number that's in a larger unit? Suppose, say, can you express this in gigabytes? Well, first of all, we know that 1024 bytes equal 1 kilobyte, right? Similarly, I could say 1024 is basically 2 to the power 10. So again, 2 to the power 10 bytes equate to 1 kilobyte. Similarly, I can say 2 to the power 10 kilobytes or 1024 kilobytes equate to 1 MB. Similarly, 2 to the power 10 MB equates to 1 gigabyte. So let's see, my MIPS memory size is 2 to the power 32 bytes, right? So let's convert this into gigabytes. So if I divide 2 to the power 32 with 2 to the power 10, I would get that my resultant number would be in kilobytes, right? So this would be 2 to the power 32 minus 10, that is 2 to the power 22 kilobytes. So again, if I divide 2 to the power 22 with again 2 to the power 10, now my kilobytes would be converted to megabytes, right? So let's do that. I would now have 2 to the power 12 megabytes. Again, if I now divide 2 to the power 12 with 2 to the power 10, my megabyte would now be converted into gigabytes, right? So I would now have 2 to the power 2 gigabytes. In other words, the answer to the question that what is the size of MIPS memory is that it's 2 to the power 4 or 4 gigabytes. And now you know how. Okay, so that was memory. So now let's talk about registers. Well, for the MIPS system that we're going to learn, it will have 32 registers. Okay, suppose your registers exist in a place called a register file. So there are 32 general purpose. There are 32 general purpose registers in MIPS. Okay, and each of these registers is capable of holding 32 bits of data. So 32 bits is equivalent to 4 bytes. Since we know 8 bits equal to 1 byte. We already talked about this here. Okay, so another term that you need to familiarize yourself with is word. So 1 word is equal to 4 bytes, which means for MIPS, a single register holds 1 word worth of data. Okay, so as I said previously, I'll repeat again that to perform any operation in MIPS, you're going to need to load values from your register. So suppose we have something called the arithmetic logic unit. So arithmetic logic unit, or ALU, which you should already be familiar with, performs operations such as addition, subtraction, logical operations such as AND, or etc. Right? So your ALU is going to be fed values from registers. So suppose if you want to add two numbers, suppose one number that's in this register and another number that's in this register, you're going to need to supply these values to the ALU from your register. And suppose you want to store the answer here, you can do so as well by telling your ALU to store the result somewhere here. Okay,